So today we will start with the last part of our mathematics for machine learning lectures. And we're going to be talking about probability theory. So we will cover the following. So we will cover the probability and random variables. So what are probabilities and what are random variables? We will cover discrete and continuous probabilities. We will cover the sum rule, the sum product rule, and the Bayes theorem, which is used heavily in machine learning. And we would also talk about some summary statistics and independence, and then also discuss a bit the Gaussian distribution, which is this bell-shaped curve that I'm sure you've all seen before. So we're not going to cover all those in this lecture, but this is the first of a couple which will discuss each of these points. Okay. So let's start by understanding what is a probability space. So a probability space models a real-world process with random outcomes. Okay, so imagine you have a real-world process, and then the outcomes of that real-world process are random. Okay, and now we want to understand something about that process, about that real-world process. So that's where the probability space can help us think. So, as examples, right? Imagine I'm throwing a coin, or I'm flipping a coin, or I'm throwing a dice, right? So, if I flip a coin, then I'm going to get heads or tails, right? And now I want to understand, this real world process, the stochasticity behind that, so I can work in probability spaces. Or if I'm throwing a dice, I can get a number from 1 to 6, right? Or if I'm observing a data point in machine learning, right, that data point maybe could have some noise inherent to it because of my sensors, for example, or because of features I didn't consider, right? So I need to be able to reason about random outcomes. And that's what the probability space would help me kind of deal with. So the probability space consists of three main components. The first component is what we call sample space, and that is denoted by this big omega, right? So this is just a Greek notation for big omega. And the sample space is the set of all possible elementary outcomes of the experiment. So your sample space, right, is like you're executing this real world experiment, and now what your sample space is the set of all the possible outcomes you can get from the experiment you are executing. So, for example, if I'm flipping a coin, right, then I could have heads or tails, right? If I am throwing a dice, I can get numbers from 1, 2, 3, 4, 5, or 6, right? And so forth. So, all these possible outcomes, elementary outcomes, they actually, from the real world experiment, they are defined in the sample space. So that's what the sample space is. It's the set of all possible outcomes that I can have from an experiment. So examples, as we just discussed, so if we're tossing a coin, right, we could get either heads or tails, right? So that's kind of all the outcomes from tossing a coin one time, right? If you just do one toss, you can either get a head or a tail. Or if you roll a dice one time, then you can get number one, that face with number one, or the face with number 2, 3, 4, 5, or 6. So that's what the sample space is. It's really just a way where we collect all the possible outcomes from the experiment that I am executing. The second thing the probability space is made of is something called the event space, right? So, when we are doing these experiments, there are events that would occur, right? And we would be interested in quantifying things related to those events. So now the idea here, right, is that we are going to introduce the sample space, which is the space of all possible outcomes, right? And then we're going to talk about the event space mathcal A, right, this tilted A, which is the space of the results that you would get from the experiment, right? So that's the space of all the possible results, right, that you would get from this experiment. Okay. So now each event A, so each event that belongs to this event space is made of elementary outcomes. So in other words, A is nothing but the subset of omega. It could be, subset of omega, or it could be the full omega itself, like if we're interested in that type of outcome or that type of event. And the set of all events, so all the possible events that could happen, are the power set of omega, which is 2 to the power omega. So let's take an example of this, right? This sounds very tedious way of describing something, but the idea is very simple, really. So the event of getting a tail, if you do a coin flip, is just this A event being equal to tails. And the event, for example, we can define if we're rolling a dice, we can define the event of getting an even number in the roll of the dice, right? And therefore now this B will be the set that includes the numbers 2, 4, or 6, right? So this is the even numbers we can get from rolling the dice. So in other words, the sample space is all the possible things that could happen, right? So it's all the possible elementary outcomes. And the event space is that subset that we are interested in. So it's the subset from the sample space that we are interested in. And that is made also of elementary outcomes. So it could be like a tail, or it could be, this dice even number in a roll of a dice. And the last thing we would be interested in when it comes to a probability space to fully understand it, right, it's actually the probability itself. So the probability which we denote by this math VBP, right, or this P. So with each event, right, each event that could occur here, right, any event that could occur here that we are interested in, so with each event A inside, the event space, there's an associated number. So there's a number which we call P of A that's between 0 and 1. And this P of A is measuring the probability or the degree of belief that the event will occur. We call P of A the probability of that event A. So in other words, right, we have a sample space, which is, all the possible elementary outcomes. We have the event space, right? That is the space of potential results, right? Like a even number in a roll of dice, or, or like a tail or head in a coin flip. And now the probability is a number we will give every event. And that number, right, is kind of our belief, or the belief of how much or how likely this event will occur, right? So it is the belief that the event will occur. So this measures the probability of the occurrence of the event. And we call that the probability of that event. And the probability is a number which could be either 0 or 1 or anything in between. It cannot be bigger than 1, right? And it cannot be lower than 0. So really what is going on, right, is that if we want to reason about a random process, right, that there is a real world process that has random outcomes, we can write all the possible outcomes that could happen from the experiment we're running. Then we can define the event space A, right, that of all those outcomes that could happen, that the event space of the events we're interested in actually measuring. And then for each of those events in that event space, we will give it a number, which we call the probability, and that measures the belief, the degree of belief of how much this event will happen. So we took an example in a coin toss where we had omega to be head or tails, and we took an example of roll dice where we had omega to be 1, 2, 3, 4, 5, or 6. Then we talked about the event of getting a tail, right? Which is, what's this event? Then we talked about the event of getting an even number when we roll a dice, for example, and this is like 2, 4, 6. This is the event we're interested in. Remember, the event, right, is made of elementary outcomes, right? So it's made of those things that exist here. And now the probability, we can give those events probabilities, right? So what is the probability of getting a tail in a coin flip? So imagine we are flipping a coin, right? So these are the possible outcomes, right? So it's this or that, right? So that's omega. And the event we are interested in is to get a tail. Now, for that event, we have a probability. And what's the probability of that event? Well, if you flip a coin, right, what's the probability? Well, you can get either heads or tails. So there are two possible outcomes, right? And then if you get a tail, it's just having this over the possible outcome. So it's a half. So there's a half chance you will get a tail and a half chance you will get a head. Now, of course, this is assuming you have a fair coin, right? Like things are equally likely to happen if you throw things in the air. Now, what about the other one, right? So, what's the probability that this would occur? You know, that if you roll a dice, what's the probability that you will get an even number when you're rolling a dice? Well, there are one, two, three, four, five, six possible outcomes, and we're interested in three of them because we want an even. So that's either two, four, or six, right? So we're interested in three of them. So the probability of that event to happen is going to be 3 divided by the total. So 3 divided by 6, which is also a half. Okay? So this is what the probability space is, right? So the probability space allows us to reason about real world processes which have random outcomes, and it will have three important things that will define it. The first is the sample space, which is the space of all the possible things that can occur. The second is the event space, so that's an event space of potential results from our experiment. And the events are made of elementary outcomes, and we have a power set as the number of possible events that can happen. And the probability is a number that we associate for every event, and it should be between 0 and 1. Could include 0, could include 1. And it's actually reflective of our belief, right, on the degree of which this event would actually occur. Now, another way of saying those things, I'm sure you've heard it a lot. So when we say the chance of this event to happen, right, it's the same as saying that the probability of this event to happen, right? So the chance of whatever is 33%, that's the same as saying that the probability is 0.33 for that event to happen. So how do you get here? You just divide by 100, right? Okay. Now, what are random variables? So another concept which we would be interested in is the concept of random variables. So in machine learning, we really don't kind of typically think about probability spaces a lot, although that's kind of the inherent set of assumptions we're making, right? But we kind of instead refer to probabilities on quantities that interest us, right? We are interested in those types of quantities, right? And rather than, in the probability space as a whole. Okay. So for us to be able to understand those things, we're going to use the notion of random variables. So in random variables, what we are really interested in is a mapping. So a random variable, a random variable A, that's a mapping from omega to the set T. So the set T, right, is a set of quantities we are interested in, right? And that mapping takes an element from omega, right? So it'll take an element from omega, and then it'll return an element in T. So let's chill a bit. Like let's think about this a bit. So what is a random variable, right? So first of all, let us understand that there's a set T, right? So this is a set T, right? That defines quantities of interest for us. So right, these are things we are actually kind of interested in. Okay. And now the random variable is this function, right, that will take an elementary outcome from omega. It'll take some elementary outcome from our sample space, right, from our sample space omega. And then it will map that to an element inside this set T, which we are interested in. We will come to a lot of examples about this, right? But just to understand, right, the random variable is gonna take, something from an elementary so from our space omega, and then we'll map that to an element in a set we are interested in, which we call t in this example, right? Now, for example, right, so we can define random variable on the set of the rolls of the dices, right? So for example, remember that we need to take an element from omega and map that to an element t, right? Okay, so imagine, this is just an example, right, which we're giving here. Imagine now that we are rolling a dice. So what is the omega? Well, the omega is either to get 1, or to get 2, or to get 3, or to get 4, or to get 5, or to get 6, right? And now we are interested in this set T, which in this case will be those numbers, 2, 2, 1, 0, minus 10, and 3. And the random variable A is going to take that that omega, and then it's going to map it to an element, right, inside the set T. So in this case, right, our set T, the quantities of interest for us, are the quantities 2, 3, minus 10, 0, and 1, okay? And now what A is doing, it is simply taking the elements inside omega and mapping them to some x inside this T set, okay? So that's really what a random variable is. It's a function that will take elements from omega and then will map them into some set T of interest for us. And now, for any of those subsets S inside this T, we have a probability for that random variable to occur. So for any subset S in T, we have PA of S, which is the probability for a particular event occurring corresponding to that random variable A. Okay. So let's kind of illustrate that. So we have omega, which is the set of all the possible outcomes we can get. So if we're rolling a dice as an example, so we have 1, 2, 3, 4, 5, and 6. And now we define this set T, which we are interested in, which is made of those numbers, 2, 3, 0, minus 10, and 1. Okay. And now, of course, here we just kind of, it's an example, so we made up this set T. In your example, this set T could be more relevant to your, specific task you're interested in. And now what the random variable is, right? So given this omega and given this set T, it's just the map, right? So it's the map that will take elements from omega and then map them to that T. So for example, if we look at S, which is equal to 2 and 3, right? So the maps that are taking me from omega to 2 and 3, if we look at them, if we have phase 1 or phase 4 or phase 6, we will get 3, right? So this 2 and 3, right, is actually corresponding, because to these elementary outcomes, right? Because 1 and 4 will map to 2, according to kind of this example we have here. And the 6, right, will map to 3. So now the pre-image of S, we call that the pre-image of S. So the pre-image are what are the things in omega that will create for me my S, right, are going to be 1, 4, and 6. That will give me 2 and 3. Okay. So why that's the case, right? Because notice that for me to get 2 and 3, I will use this definition or this example I made here. So I will have A of the roll of the dice, I get 2. If the face is 1, A of 4 is 2 if the face is 4. And 3, I will just have A of the face is 6 is equal to 3. And now, what are the things that from omega that will give me the set values 2 or 3? Well, they're going to be what we call the pre-image of this set S, which is the subset of T. And in our example, they're going to be 1, 4, and 6. Okay. And now notice that the probability of this S to happen, right? The probability of this S to happen associated with the random variable A, of course, right, is the same as the probability of the pre-image to happen. Okay, so if we're interested, right, in the probability of this S, which is 2, 3 in our case, right, if we're interested in that, this is the same as us saying, I'm interested in the probability of the pre-image, A inverse of S, that will take me from here to there, right? And now, what is the probability of A inverse of S? Well, the probability of A inverse of S is really the probability of getting this, this, and this. So now to get this, I have 1/6 of a chance if I'm rolling a dice. To get this, I also have 1/6 of a chance. And to get that, I also have 1/6 of a chance. So in reality, this is like the probability of getting a face of sixes, the probability of getting a face that has 4 dots or number 4, and the probability that has 1 dot. So that'll be 1/6, 1/6, 1/6, which is a half. Okay. And now, so notice that the random variable A, right? The random variable A defines a probability distribution on that target space. Okay. So to recap, right, what we've done so far, we defined the probability space as the space of omega, all the possible outcomes, the event is space A, and then we said there's a probability associated with every variable, with every event A. But then we said that we're really interested in more, not just the whole probability space, but quantities of interest for us. So we introduced this set T, which defines our quantities of interest. And then we defined a random variable, and that random variable was the map, right, from elements in omega to elements in T. Okay, and then we gave an example here. So we said, okay, imagine my set T is 2, 3, minus 10, 0, and 1. And now I can define a random variable A as follows. So it's a map, right? It's a function that will take elements in omega and put them in T. And then I said, okay, I will have for this face A of that elementary outcome for a dice roll is 2. Also, when you get a face 4, from the roll of the dice, you will get 2. Or when you get a face of 2, you will get 1. Or you get a face of 5, you'll get 0, and so forth. And then we define our random variable in this way. And then we said, so pictorially speaking, right, there's this omega, which is the set of all the possible outcomes from rolling a dice. And this is T, which is the quantities of interest. And again, we made this up, right? This is just an example, right? This is the set T we are interested in. And then here we said, okay, if we are interested now in a subset of that set T, then we can consider or understand it via its pre-image, which is A inverse of S, so kind of the inverse of this mapping. So in other words, what are the omegas that would have led to 2 and 3? And then we said that that random variable A will define a probability distribution, right, over the S on the target set T that we're interested in. So in other words, right, for that random variable A, you will be able to define a probability on S, and the way you would define that is via the pre-image of it, as we did in this example. Okay, cool. Now, since we have those definitions, we can start talking about probability distributions. And I think in these examples, or now once we go further, it'll become clear what this set T is and so on, because maybe before it was too abstract. But now let us say, okay, we are working in a world, where we can enumerate all the elements in the target set T. Right? So I can enumerate all the elements in my target set T. Okay. So in other words, T is equal to, x1, x2, x3, x4, xk, and so forth. So I can actually enumerate all of them because I'm in a discrete space, so I can list them all. Okay, so that's that, right? So now we are working in this space where I can enumerate, right, all the elements in the target set T. Now, a random variable A defines a probability distribution on T. Remember, right? The random variable A, I mean, as we said here, right? So the random variable will define a probability distribution, right? Okay. So now the random variable on A, okay, defines a probability distribution on T, okay, such that for any xi in T, so for any element in this set T, its probability PA of xi is nothing but the probability that that random variable A takes the value xi, okay, that is equal to PI, okay? So let's go slowly through this. So imagine you can enumerate all the possible elements in the set T. And now let's say we have a random variable, and that random variable will define a probability distribution on T. Now, what does that mean? It means that for every element xi inside this T, we will have this associated number between 0 and 1, right? Equal to 0 or equal to 1, as we're included. And then we would call that PA of xi. Now, when we write this notation, PA of xi, it means we are saying that that's the probability of the random variable A to be equal, to xi. And then we denote that by small p of I. Okay. So in other words, right, a discrete random variable, it has what we call a probability mass function. That probability mass function is the collection, right, of all these probabilities, P1, P2, P3, P4, P5, up to whatever, that we can list. So for each of those events, x1, x2, x3, up to xk, and so forth, right, we will have P1, P2, P3, P4, up to pk, okay? And now therefore, we can characterize sorry, the discrete random variable by a probability mass function, which is the list of all the P1, P2, P3, P4 up to Pk. So in other words, is the probability that the random variable takes the value x1, the random variable takes the value x2, the random variable takes value x3, and so on, right? But we have some, properties of this. So we need each of those PIs to be greater than or equal to 0, and we need their sum to be equal to 1. So the sum of all the possible things that can happen, the probability of that happening is just the sum of all those things, which should sum to 1. And the probability cannot be a negative number, right? So therefore, it should be greater than or equal to 0, okay? So now once we have a random variable which defines a probability distribution on the set of things we're interested in T, then we can characterize that random variable by a probability mass function, which is the set of all the probabilities P1, P2 up to whatever elements we have enumerated, such that each of those probabilities is greater than 0, greater than or equal to 0, and their sum is equal to 1. So let's take an example of this, right? So an example of this is a Bernoulli random variable, okay? So a Bernoulli random variable, so we say A is a Bernoulli random variable of P, right? So A is a Bernoulli random variable of P. What we actually mean by that is that, first of all, right, the Bernoulli random variable are defined over a set T, which has two possible x's. So x1 is equal to 0 or x1 is equal to 1. And the probability of A is of 1 is the same as saying, because see, probability of A of 1 from here is the same as saying this is the probability of that random variable A to take a value equals to 1, which is equal to P in this case, according to the Bernoulli distribution. And the second xi is 0, right? So the probability of A equals to 0 is the same as, or the probability of A of 0 is the same as probability of A equals to 0, which is equal to P2. But notice that the sum of P1 plus P2 should be equal to 1. So 1 is P, the other one should be 1 minus P. So let's just go carefully through that. So notice that, first of all, in our case here, we have t to be equal either 0 or 1. These are the things we are interested in, right? So for example, imagine you're analyzing a coin flip, right? So you either get a head or you get a tail, right? And now for the random variable, for the head, like let's say you can map that to 0 in t, and for the tail, you can map that to 1 in t. So this is the t we are interested in. And now, because we have that random variable and we have this set t, then that random variable, right, it will already be characterized by a probability mass function, right? So that's the probability mass function, which is, the probability of P1, P2, P3, and so on. But in our case, we only have P1 and P2, right? So now P A of the first thingy, right, is equal to P of A equals 1, right? Where did we get this from? Well, we got this from here, right? And then that is equal to P1, which is equal to P because, we have a Bernoulli distribution with a P here. So the probability for us, for that random variable to be equal to 1 is nothing but P. Now, what about the other event, which is the probability under A of 0, right? Well, the probability of A under 0, that's the same as saying the probability of A is equal to 0, right? Which you can definitely call P2, I can say, okay, that's P2, sure. Because, I told you from here, you will need to call P1, P2, and so on. Okay. But now notice that these things sum to 1, right? So P plus P2, right, should actually sum to 1. So therefore, right, P2 should be nothing but 1 minus P. And that's why you get here 1 minus P. Okay? So this is this is an example of this case, but of course there are other types of probability distributions, not just the Bernoulli distribution. So here's an example of a Poisson distribution, right? And that Poisson distribution is kind of written in this way. For now, it's not extremely crucial to understand what the equation of the Poisson distribution is, but just note that for these random variables, which are discrete in this case, we can define different types, right, of probability mass functions, right? So a Bernoulli, a Poisson, there are other things as well. Okay, right. Now we switch a bit to talk about the joint probability of random variables. So imagine you have discrete random variable A, which is a map from omega to t, but then you also have another discrete random variable B, right, which is also a map from omega to t. And now let's take two x and y, they both belong to t. Now we can ask, what about the joint probability, right, of those two random variables A and B? So what is the joint probability of A equals to X and B equals to Y? So what's the joint probability, that A will be equal to X in T and B will be equal to Y in T? The way we write this as the probability of A comma B of X comma Y, right? So that's how we write the joint probability distribution for the random variables. Okay? And what does this actually mean? Well, it means, right, we are looking for the probability of those omegas inside my big omega set, such that A of omega is equal to X and B of omega is equal to Y. So let's understand this. So notice that A and B are random variables, right? So what they're going to do is they're going to take values from the elementary set of outcomes, omega, and they're going to map that into this set T of things we are interested in, right? So now here, you will see that A of omega, right, is a map that will take omega and then will give me something inside t. Now, when I say what is the joint distribution of or the joint probability of A and B for these X and Y's, it means I'm looking for the probability of those omegas such that that random variable will take that omega from this set and map it to X, and the random variable B will take omega from that set and map it to Y. And that's what the joint probability distribution actually means, right? So the joint probability distribution is that we are going to be interested, right, in in the probability of that event that will actually map these two random variables, right, to two elements in the set T we are interested in. So we're going to be saying the probability of A and B. And when I say A and B, or I say the joint distribution, or I say the joint probability, they're actually the same thing. Now here what we have is PA and B of X and Y is simply the probability of those omegas inside this omega set such that A of omega is X. So you take that omega and then you map it through the random variable A to get X, and B of omega is equal to Y. So you'll take that omega, or you're looking for that omega that you will put through B, and then you will get Y. All those omegas inside this big omega set that will make A of omega is X and B of omega is Y, that's the event we are interested in. That's the probability we are looking for. So, in other words, imagine we have our omega, here, and we have the set T, and we have those two X and Y's we are interested in. Now, notice for this X, its pre-image is A inverse of X. So we discussed what the pre-image is, right? Remember, let's go back a second. So we talked here what the pre-image is, right? So the pre-image is those things inside omega that will lead to the value in T we are looking, or we are interested in. So for this value X, we can look about A inverse of X, which are all the omegas here that will get me to X. The same we can do to Y. So we can take its pre-image, which we call B inverse of Y, right? And then this is the pre-image that would actually map things in omega to that value Y. And when we are looking for the joint distribution, right, what we're really looking for is the intersection between these two sets. So when we are really saying the probability of A and B of X and Y, we are just saying or asking the question, what is the probability, right, of the intersection set of the pre-image of that X and the pre-image of that Y? Okay. So to repeat, imagine we have T and we're interested in X and Y, right? Now we can get the pre-images of the X and the pre-images of the Y. And those are all the things in omega that will give you X and will give you Y. And now when you are looking for the joint, you're just looking at the intersection. You're saying, okay, which ones in that intersection, what's the probability of those events that happen in the intersection between the pre-image over A and the pre-image of B? And that's what the joint probability is. Okay, so let's take this example again. So let's say we have a random variable A over, again, so this is the example of me throwing a dice. And then I will have a random variable A, which will take, the elementary outcome of having a face 1 on the roll of the dice to be 2, 4 to be 2, 6 to be 0, 2 to be 1, and 3 to be minus 10, and 6 to be 3. And then let's also define another random variable B, which again acts on the on the elementary outcomes, but because it's another random variable, right, it could have different values, in the set T, right? It's another random variable, so it can have a different value in the set T. So here, for example, for the one face of 1, when you roll the dice, it is 1, but here A was 2, so they're different random variables, right? And when it was 4, we also get 2. When it was 5, we get 0. And when it is 2, well, this gets 2, and so on. And now let's say we are interested in this X and Y in T. So let's say we're interested in 2 and 1. So now notice that A inverse of 2, right? So A inverse of 2, what are the things here in omega, right, that will give you 2? Well, you will either have this set right here, the face of 1, or it should be actually the face of 4, I suppose here. This is a typo, sorry. But those are the ones that would give you the value 2, because you see 1 and 4, they will give you the value 2. And now for the y equals 1, what is the pre-image that will give you 1? Well, if you look at the values of the random variable, you will only get 1 when you have a face of 1, right? So therefore now, the pre-image to get the value y is equal to 1 is just this face when you have 1. And now, when we look at the intersection between these two sets, well, we notice that 1 is the intersection between these two sets, right? So that's the intersection between these two sets. So now, when I write what is the joint distribution over the A and B, so what's the joint distribution for the random variable A to take equals to 2 and that equals to 1, is just the probability of having this face when you roll the dice, which is just 1 out of possible 6 rolls. Okay, so let us reiterate this a little bit just to fully understand it. So we can define a joint probability of the random variable and two random variables, or of other many random variables, but for now we're considering 2. And to define that, right, let's say we're talking about discrete random variables for now. We will take 2 discrete random variables. One is A, one is B, and we will take 2 elements in the set T we are interested in. And now the joint probability, right, of these 2 random variables will be the probability of those omega in the set of possible outcomes that will make the value of the random variable A equals to X and the value of the random variable B equals to Y. So now, intuitively speaking, right? Intuitively speaking, right? We said we are going to look at it in the following way. So if we had omega and we had T, and now we are interested in X and Y inside T, right? What we could do to understand this probability, right? Because we want to find all those possible outcomes, that will make A omega equals to X and B omega equals to Y. Well, to understand that, we can construct the pre-images, right? We can go back to the omega space and find which of those events in omega would actually lead me to the value X inside T, and which those parts of omega will lead me to the to the value Y in T. So in other words, we're computing the pre-images of X and Y in the omega set. So we take X and then we can compute, let's say, A inverse of X, which is the pre-image. We can take Y and then we can compute B inverse of Y, which is the pre-image. And now we want those omegas, right, such that both A of omega is X and B of omega is Y. So in other words, I want the things at the intersection, right, between these 2 pre-image sets. Because at that intersection, right, we will have components from A inverse of X and components from B inverse of Y that would actually map to X and Y together when A inverse of X is equal to those things and B inverse of Y is equal to those things at the same time. And now, therefore, this joint probability is nothing but the probability of this intersection between the 2. Okay? And then we've taken an example of this, right? So we defined 2 random variables here, A and B, and then we were interested in 2 and 1. Then we listed the pre-images. We had a typo here, I think, which should be 4. We have listed the pre-image A inverse of the 2 we are interested in and B inverse of the Y we are interested in. And then we found the intersection, because that's what we are interested in, right? It's the intersection. And then we said that the joint probability of these 2 random variables to be equal to 2 and 1 is nothing but the probability of the intersection between the pre-images, which is this, which is equal to 1/6. Okay? So now In the next lecture, we will talk about the conditional probability distributions and also some marginal probability distributions. But for now, we have discussed what is a probability space. We also discussed what are random variables, discrete random variables, and also talked about the joint probability. So please ask questions in the comments if you have any, and do please subscribe, like, and share this video for us to continue doing those lectures. So with that, I will end this video, and then I will see you next time. Thank you.